This is Unit 5, Analytical Applications of Differentiation, Lesson 1, Mean Value Theorem, Part 1. So what we're going to do is we are going to look at the mean value theorem and a sub-theorem of it, a special case of it, which is Rolle's theorem. This is another existence theorem that we have, kind of like the IVT. So what the mean value theorem talks about is when you're talking about mean, you're talking about average. So we're going to be looking at average rate of change and what that can do for us, not to us. So what we're going to do is we're going to do the steps at the bottom. So step 1 says to draw the secant line for each figure on the given interval. So we're going to look at the 2 points that are given and we're going to draw the secant line. So our first secant line, hopefully I can do these kind of straight. It's going to be like that. There's our secant line. And so on the next graph, g of x, my secant line will look like that. For the third figure, my secant line, I'm going to have 2 of them. I'm going to have one across the curved section here. And then I'm going to have one, whoops, that one was really bad. One from the second point to the third point here. Those are my secant lines. And then for the last curve, my secant line is going to be like that. Okay, so step 1. Then step 2 says, are there any points on the graph of each function where the tangent line to the graph appears to be parallel to the secant line you've drawn? Draw the tangent lines between the endpoints of the given interval if possible. So what we're going to do, and call that point of tangency part C. So what we're going to do is we're going to find a point. So if I go along this curve, what I can see is there's a point like right here. Let me use a different color. Right here, that looks like if I draw that tangent line, it's going to be parallel to the secant line. Like that. And there's another one like right about there. Okay? Because I want this to be parallel to my secant line. So here I have a C that, I don't know, is approximately, let's say 2.5. I'll label that C1. And since we have a second C, we have C2, which is around 2 or 3. Okay, so doing the same thing on the next graph, what we notice is that there isn't a point on the g of x graph. There's no point on the curve where we're parallel to the secant line. So in function at h, we have 2 points again. We have one that's along the curvy part, like right there. Okay, we'll call that C1, which is approximately equal to 3. And then there is one down at the bottom here that's parallel, that doesn't look parallel, that's parallel to that second secant line. That's a little better. And we'll call this C2, and that's approximately equal to 6. Okay, and then our last one, we have 1 point, which is right around 4 here, that point right there. So C is going to be 4. Okay, and then now what we're going to do is take a look at these values that we have. So which functions are continuous on the given intervals? Well, that would be, we have 3 functions that are continuous. We have f of x, which was the first graph. We have the second graph, which is g of x. And we have the last graph, which is k of x. H of x had a jump in it, so it is not continuous because we have a jump right there. Right there we have a jump. Okay, which functions are differentiable on the interval? Well, there are only 2, and those 2 are going to be f of x, because that was a nice smooth polynomial curve, and the last graph, k of x. And I'll write it down in a second why the other two aren't. Now, g of x has a cusp right here in between the 2 points in the interval, so that is not differentiable on the interval. And as we said before, h has a jump in the interval, so we don't have a continuous function there. And even though we have a cusp in k of x, our second point is at that cusp. So the way we're going to define this is that it's going to be differentiable. I don't know what just happened there. It's going to be differentiable on an open interval, so it's not going to include the endpoints. So if I don't include that second endpoint, then k of x is continuous and differentiable on that interval. Okay? So why aren't they differentiable? So g of x has a cusp. And in the second interval of h of x, it is not continuous, there's a jump. So what we have done is we've set up the conditions for the mean value theorem. So this is another theorem where you have to show that the conditions exist first. So here's the mean value theorem. So if f is continuous, and this is what I was saying, on a closed interval, so it has to be has to be continuous on the closed interval, including the endpoints, but differentiable on the open interval. Okay, so if you notice now, we're not including the endpoints, so that cusp in k of x didn't matter. What we're going to find is there's some number c, and I'll label it in the picture here. Here's the c, such that the slope of the secant line, so here is A, which for some reason didn't get labeled on the graph. Here is B. So the slope of the secant line is going to be the same value as the value of the slope f of c here at some f of c, because these are parallel lines. So they have the same slope. So there is some point, if you have a continuous function on a closed interval and a differentiable function on an open interval, this shows the existence of a c, but not exactly where it is, in that interval, that the slope of the secant line will equal the slope of the tangent line, or the derivative of the function at point C. So verbally, the instantaneous rate of change equals the average rate of change at C. That's the important part. And the tangent line is parallel to the secant line at C. Okay, now Rolle's theorem, that's our mean value theorem. Rolle's theorem is a special case. And here's what the special conditions are for Rolle's theorem. We still have the same conditions. F has to be continuous on a closed interval and differentiable on the open interval. Since it's a subcase of the mean value theorem, the same conditions have to apply. Now, here is what we're adding. Now we're saying that the endpoints have to be the same in the interval. The f of A and the f of B have to have the same value. So what happens then is we've created a horizontal secant line. So now what we have done is we've created a place where the tangent line is 0. Okay? So this is telling us that if these conditions hold true, there's at least one number between A and B where we have a horizontal tangent line. This is going to be very, very important to us going forward, finding horizontal tangent lines. So a little note here, both Rolle's theorem and the MVT guarantee at least one value on the open interval. Now again, they're existence theorems. They don't exactly tell you what the point is. There is ways to find them, and we'll get into that as we go through this unit. Now, what are the differences between the two, just to summarize them? The differences are that Rolle's theorem requires f of A to equal f of b. That's an important condition difference. And that the slope of the secant line has to equal 0. If my memory serves me correctly, I didn't look it up, I think Rolle's theorem came first, and then the mean value theorem got expanded afterwards. So he found that special case, and then mathematicians looked into it and said, hey, well, what if it isn't 0? What kind of conditions have to be met? What can we find out? Okay, what does Rolle's theorem tell you must exist on a given interval? This is what the important part of this is. This shows the existence of an extrema, a max or a min, in the interval. Now, we've already seen why these are important in some of the application problems we've done, because we can tell from max and mins, how to maximize our profit. When is it at its maximum velocity? Things like that. So it is important to be able to find these max and mins, and so that's why Rolle's theorem comes in very handy. We are to plot this sketch this graph from the plots. And we are told in the description that it is a continuous differentiable function in this interval here on the grid. Okay, so let's go ahead and do that first, and then we'll answer the questions below. Okay, so here's our curve, and now we are going to answer some questions about it. Okay, so question A asks us to find the average rate of change of g of x on the interval 2 to 9. Okay, so let's highlight those points. So here is 2, 4, and we have 9, 11. So what we're doing is we're finding the slope of the secant line. So let's go ahead and draw that. Okay, so here's 2, 4, and here is 9, 11. All right, so let's go ahead and use that information to do this. So our average rate of change is going to equal 11 minus 4 over 9 minus 2. And so we get 7 over 7, which is 1. Okay, so there's that. Part B says, is g prime of 6 equal to the slope of the secant line from part A? Justify. Okay, so let's use, like we've done before with tables, let's use 2 points on either side of 6. So let's use 4, 8 and 7, 13 and find that slope, and should be close to the slope of g prime of 6. So let's go ahead and do that. So we're going to do that. G prime of 6 is approximately equal to, so I'm using these points, 7, 13 and 4, 8. So it's going to be 8 minus 13 over 4 minus 7. And when we do that, we get negative 5 over negative 3, which is 5/3. So we can say no, g prime of 6 is approximately equal to 5/3, which is definitely not equal to 1. That's not even close. Okay, next question. Does Rolle's theorem apply on the interval 4, 9? Explain why or why not. So you would say that Rolle's theorem does not apply since f of 4 is equal to 8, which is not equal to f of 9, which is equal to 11. Okay? They don't have the same endpoint y values. Okay? Is there another interval where Rolle's theorem applies, justify. So you can say yes if you look at the interval 4 to 11. At x equals 4, we have this point, 4, 8, and at 11, we have 11, 8. And so you can say here, before I put the and there. So you can say here that f of 4 equals f of 8. And then we have another situation on the interval 11 to 15. We have, because we have f of 11 is equal to f of 15. And both of those are equal to 8. And you also want to say that g of x is continuous and on the closed interval and differentiable on the open interval. Remember, this is an existence theorem, so we have to make sure that the conditions are met. And I'm going to stop here and continue in the next video.